Hi everyone, welcome to another Q&A about history of science and technology. I am not in my natural habitat today, so all sorts of things could go wrong, but we'll hope for the best. Let's see, all sorts of questions here. Doug asks, has any species evolved in a measurable way since humans have been observing and tracking evolution? Well, there's certainly some macroscopic examples of that. I mean, people always used to quote a certain kind of moth that as a result of pollution, trees had gotten darker. And so the moth that was darker was better camouflaged. And quite quickly, moths ended up being like that. But if you go beyond sort of the big critters, there's plenty of evolution that gets observed all the time. For example, the bacteria in our guts, our gut microbiome, is always evolving. And in any given person, it evolves quite rapidly. And depending on what you eat, it will evolve differently. Not particularly well understood yet, but that's something where you get to see evolution even within a single person. Same thing with tumors. Within a single person, this is one of the sort of bad stories of tumors, is that there will be evolution. You apply some chemotherapy agent. I told you something might go wrong. This froze horribly, but we seem to be back. Well, now you can probably see me again. Can you? Okay. Well, we'll hope it doesn't freeze again. Okay. In any case, in things like tumors, you can get the situation that you apply some chemotherapy agent, and the tumor cells will evolve to avoid that. Same thing you see, actually, there are these nice experiments where you can see you have a plate and you have some bacteria growing on the plate. Oh, this is frozen again. Oh, bad, bad, bad. All right, let me try changing something here. Sorry, I think we have to stop video and okay, hold on 1 second here. Okay, let's see. I think we're back again. Let's see whether this fails again. Up, we're back again. Let's see whether this fails again. We were just talking about evolution you can see. And I was mentioning experiments where you have bacteria on some plate and you start putting down antibiotics and things, you can actually see sort of different colors when you've stained them and so on, of bacteria that successfully evolve. They make little fingers where they're kind of one particular sort of strand of bacteria will evolve to avoid the antibiotic, and then they'll keep going, and then there'll be more and more of those, and then you put down some other antibiotic, and then more and more of those, and so on. And so you can really see evolution happening in a very direct way in cases like that. I mean, evolution is a bit faster for creatures with asexual reproduction, like bacteria and so on, than it is for creatures that have, well, I mean, it probably helps also that the time to replicate the bacterium might be 20 minutes or an hour or something like that, as opposed to much longer periods for bigger critters. I think I've certainly heard of claims of lots of bigger critters who evolve over a very small number of generations to change their characteristics in response to some environmental change. I mean, it's worth realizing that when you have both genomic evolution and you have kind of evolution in the learning that happens in a species, so to speak. So in a sense, the genomics, you're locked in for a given generation, but what you learn is something that can change even as sort of the fashion changes, so to speak, or the herd goes in a different direction. And that's something where you've got both the genetic evolution and the kind of evolution of the memes, so to speak, that are sort of separated from that. The sort of the cultural evolution is separated from the genetic evolution, and that can happen on an even faster timescale of the creatures learn how to sort of get their food by opening this door or something, and then that gets passed on to the young creatures, independent of kind of the genetics, independent of natural selection operating. I mean, one can ask the question, when one looks at kind of the mechanisms of natural selection, it's people have kind of, well, there's sort of a question, what's the fundamental theory of natural selection? I mean, the idea that originated with Darwin, that, well, people had precursors of this idea, that the species we have now are the ones that made it through kind of the gauntlet of having had the most kind of children, so to speak, and the forms that didn't make it are the ones that had been unfavorably selected by the characteristics of the environment or the other creatures in the ecosystem, or whatever else. And that was something that I think Darwin really understood with clarity for the first time. I mean, Wallace was sort of on the track too, but that was something that was sort of a mechanism of, you get what you get because that was the thing, because there's this mechanism of natural selection where the form of the environment determines what you get. Now, at the time, there was plenty of artificial selection. People had been breeding all kinds of domesticated animals and pigeons and all sorts of other things. Darwin had all sorts of correspondence with pigeon fanciers and so on, who'd been breeding types of pigeons and so on. So it was very well understood that you could breed creatures to have particular characteristics of, the fluffier cat or whatever else. I'm not actually completely sure that cat breeding was a big thing yet by then, but in any case, but the idea of artificial selection that breeders had been doing was well understood. The thing that Darwin really added was the idea of natural selection, that the environment of the world could determine what species would be successful and what would not. But sort of the question of could you turn that into some kind of quantitative theory of what was going on, that was a different question. I mean, Darwin famously sort of thought that this process of natural selection was the thing that led to all the sort of amazing complexity of life on Earth. And he has the last sentence of Origin of Species, his book from 1859, says something like, as the Earth keeps circling around the sun according to the fixed law of gravity, so species have been and are being evolved. So his kind of concept was, just like kind of this law of gravity that that was something that one sort of believed was a global feature of science. So this phenomenon of natural selection would lead to progressively more complex organisms. There's never been evidence that that's true. And the fact is there are pretty simple organisms that have been pretty successful throughout biological history. And does not seem to be a necessary feature that sort of you have to get more complex organisms to be more successful. Now, it's an interesting question whether in a situation where the organisms are competing with each other, whether that sort of forces one to have somehow a more complicated program for the organisms. That's still something, I think, to be determined. But Darwin at the time didn't really have a kind of a hard science kind of mathematicized version of what natural selection meant. In fact, there's a nice picture, sort of a sketch that Darwin drew of kind of a tree representing the different sequence of organisms. His son, Francis Darwin, I think it was that son, was kind of more mathematically inclined, and that was kind of and Charles Darwin worked a bit with him on these kinds of questions, but never really got sort of a mathematicized formalization of the idea of natural selection, and nor has anybody since, really. I mean, there are a lot of details about kind of using game theory and things like that to figure out. I mean, that was something that was very popular in the 1950s and 1960s. After the development of game theory in the 1940s, game theory had been developed for economic purposes and sort of strategic military purposes. Of kind of, there were these sort of payoff matrices of how well would you do if you played this versus that against your opponent, and that kind of idea turned out to be a good representation of sort of the competition between members of a species and so on, and that led to all sorts of predictions about sex ratios in different kinds of species and so on. That was, I guess, had matured by the early 1980s, because I interacted a bunch with a bunch of those kinds of people who were very proud of the fact that they'd successfully sort of mathematicized this aspect of biological evolution. I think this whole question of kind of to what extent can you sort of formalize it is an interesting one. Another thing that was sort of a different branch was the idea of genetic algorithms, the idea that you could have programs where you would get to the program you wanted by doing some kind of artificial selection, where you say, this program isn't quite right, let me modify it. Even the idea of not only mutations in the genetics, the program being the sort of the genome, not only mutations in the program that are things like single mutations, point mutations, but also things like crossover of the kind that happens in sexual reproduction, where you're taking a big chunk of genome and you're putting it, you're sort of copying it over to another, you're taking two different parents and you're sort of mixing together big chunks of genome from one parent or the other. And so a bunch was done on both first genetic algorithms, genetic programs, genetic algorithms, trying to sort of see whether you could sort of evolve to a successful program by just applying constraints. And there were a bunch of successes, particularly in the 1980s and so on, 1990s, successes in designing analog circuits, kind of the big names in this area, both of whom I've known, John Holland and John Koza. John Holland more on the kind of genetic programs, John Koza more on the genetic algorithm side of things. And there were many kind of applications for sort of computer game kinds of purposes and so on. I think in the end, it's the sort of some successes in that area. One can think of kind of neural nets as being, and what's done with training of neural nets as being sort of a big version of something a bit like that, except that in typical genetic programming, the programs are somehow discrete, whereas in neural nets, there's kind of this idea, at least in sort of the current neural nets that have evolved from the 1943 McCulloch-Pitts neural nets, there's the idea that the weights are continuous numbers and you can kind of tweak them incrementally in a sort of calculus-like way. And that the thing that in genetic programs, genetic algorithms, and so on, the one of the issues is a program is something you write in terms of discrete, typically is something you write in terms of discrete constructs. And so what does it mean to make an incremental change? That's a tricky issue. I have to say, actually, I've recently been doing some experiments on this myself, because I'm sort of curious, what is the minimal model that you can make for biological evolution? And you can have very simple programs where you can say, can I reach this particular objective? Can I make the program do this funky thing? And how do I get there? And what you see, and it's very typical of sort of what you see in machine learning these days, you can invent a kind of a loss function that says, how far away is this program from achieving what you wanted? And then you can say, as you sort of evolve the thing, how much can you reduce that loss function? And so when you deal with neural nets, you have a lot of strategies that involve backpropagation and calculus and derivatives, automatic differentiation, all this kind of thing that tries to kind of know exactly how you tweak the structure of the quotes program, in the case of neural nets, the weights and so on, to achieve the objective you want. But there's a much stupider thing you can do, which is what biological evolution seems to do, which is you just randomly make changes and you see what happens. And so you can ask the question, if you're in some state and you've got a program and it's not really doing what you want, but it's kind of close, can you just try 100 random mutations and just see which one does the best of those, or maybe the one you already had did the best. But let's say you have one of those other ones that does better, then you pick that one, you bet on that one, and you keep going, and you see whether you can evolve to actually be able to satisfy the constraint. Now, as stated like that, it's a very simply stated problem. In reality, it's more complicated than that. Because in reality, you don't just bet on one organism. There's not just one member of a species that's the sort of carrier of this is the creature. If this species is going to make it, this is the one member of that species that exists and is going to sort of have progeny and things like this. Instead, you have a whole range of members of the species, and at any given step, you're kind of betting on many organisms, and you're seeing what happens to each of those, and the one that you thought was last may come out first in the next generation. The kids may be smarter than the parents or whatever else, or better than the parents. Even though the parents were kind of lame, the kids may be really good. And the parents who were great may not have kids who are only as great as they were, rather than being able to jump ahead and so on. And so the definition of what's going on gets considerably more complicated when you start dealing with, it's not just the best of this generation, it's several different sort of members of that generation and so on that you have to sort of carry forward. And I think one of the things that's interesting is you might just get stuck. You might get to a point where it's kind of like you've evolved to this point and there's just no way to get better. You're in this sort of basin where, in this mountainscape of, can you get to the top of a mountain or the bottom of some bottom of the hill, so to speak, and there's just no way to get there because you're stuck in this kind of area with a bunch of walls around it. The thing that tends to happen, and I think the main sort of trick that biological evolution uses and that neural nets and machine learning use, is by the time you have enough parameters, the chances are there's some direction to go in that gets you to the better place, so to speak. And I think it's the very complexity of biological organisms that makes it possible for evolution to work. If organisms were much simpler and you just had 3 parameters to tweak, it'd be much harder to actually escape the goofiness or something and get to the point where you have something better happening. So anyway, a few thoughts about observation of biological evolution, and it'll be an interesting thing to see whether one can more successfully, in a sense, formalize the process of evolution and the description of sort of how what is really going on in evolution. My friend Greg Chaitin, the originator of kind of algorithmic information theory, has kind of an approach he calls metabiology, where he's asking questions like, if you have a program that, for example, runs for a long time and then halts, and your sort of fitness function is run for the longest time and then halt, one of the features of that is there's never a program that is the all-time winner. There's never a point. You can always make a program that runs for longer than any program before and then halts. The program will be progressively more complicated, but you'll never sort of run out of possible programs that will always do better than the ones before. And in fact, as you start looking at the kind of the how long it can go before it halts, you're kind of ascending into numbers that are sort of absurdly large and even in some sense not computably large. So it's kind of a model for there's always a better organism. You never, if that's the fitness function, you'll always find a better algorithm, a better organism. So it's kind of like there's no end point, there's no limit to biological evolution. I think one of the things that's sort of an issue in this kind of modeling is one thing is what's the environment of the world? What are the niches that organisms can exist in? Do you say there's a fixed set of niches and the organisms are going to optimize themselves relative to those niches? Or do you go even more complicated and say, given that there are these different organisms that are interacting with each other, how does that then work? And do you get a situation where sort of this collection of organisms is the only one that you can get to, and you'll never get to a better place where there's another sort of branch organism that gets even better? I think the sort of the intuition from this sort of metabiology approach and from thinking about sort of evolution computationally is there's never an end to evolution. There's always a way to make something better, so to speak, and with any definition of better. And that's something which is still for the future to really formalize what all of this means. And perhaps that formalization will be important for some of these cases of very rapid evolution, whether it's in the microbiome, in tumors, in antibiotic resistance, these kinds of things, or for that matter, in viruses, which also have very fast evolution. And I mean, just to be clear, I think the original question was about have we observed evolution happen sort of on human timescales? Well, absolutely. In the case of the COVID virus, SARS-2 virus, there were endless trees that were drawn about this is the evolution of all these different strains of the virus. And it was like, here was the actual person in which that new strain developed and so on. And then you got to see the more and more complicated tree of what happened. Let's see. There's just one comment here, but this is more about general science than history of science, but I'll talk about this anyway. Sigint asks, there's more bacteria than blood cells in us humans. Why? You know, it's always a funny thing. You talk to people who study kind of, I don't know, biology, physiology of mammals like us, and they say, you know, there's so many cells, there are trillions of cells in the body, and we study all these different things. Then you talk to people who study prokaryotes and bacteria and so on. They say, by the way, you should know there are more bacterial cells in a human than there are eukaryotic human cells in a human. And then you talk to people who study viruses, and they say, by the way, you should know there's more viruses in a human viral pieces of virus, the little viruses, than there are bacteria, which is again bigger than the number of sort of human cells. So it's partly because the bacteria are smaller than human cells, viruses are smaller than bacteria. I mean, human cells have a huge range of different sizes, from giant muscle cells to little tiny red blood cells and so on. Very great range. I mean, even though it's the same DNA, what's transcribed, what actual proteins get made is very different in different tissues and so on. The question, I think there are probably more bacteria than blood cells because they're smaller. And it's probably as simple as that. Let's see. Jamie is asking, this is again about evolution. Have humans aided in the evolution of domestic animals? Well, gosh, I mean, humans have done a lot of artificial evolution. I mean, the one case of artificial evolution is that one might consider controversial is things like gain of function mutations for viruses and so on. That's a case where artificial selection was used to kind of pick out the virus that was the winning virus. In terms of domestic animals, well, yes, people have created all kinds of different critters the dogs that have this characteristic or that characteristic, the cats with this characteristic, that characteristic, the snakes with this kind of different pattern on them and so on. And, can you make a snake? People haven't gotten to the point where they can make a snake that spells out somebody's name on the pigmentation of the snake. But and that's sort of a challenge for theoretical biology, I suppose, to say, could you imagine doing the reverse engineering? If I want the snake to spell out hello and to, grow to have that pigmentation pattern, can I figure out what I should put in the genome to make that happen? And we're not there yet. But in I think that's part of the story there. Let's see, other questions. The question from without here, have all of Grothendieck's works been understood yet? Okay, so Alexander Grothendieck was a mathematician, French mathematician, who was probably one of the most abstract, successful mathematicians that there's been. And he invented kind of a way to really think more generally and more abstractly about lots of kind of areas of mathematics, bringing together these areas of mathematics. I mean, basically what happens in mathematics is you'll have something like algebra, you'll have something like geometry. Well, it was known since Descartes, since the 1600s, that algebra and geometry have some sort of common, you can represent geometrical things algebraically, some algebra you can represent geometrically, and so on. But as we look at different areas of mathematics, algebra, geometry, topology, all these kinds of things, there's a question of sort of what are the common themes between these different areas? And I guess Grothendieck's big contribution was getting to a level of abstraction at which these very different areas of mathematics seem to have common themes. And I think that's sort of one branch, a somewhat different branch originating in the so Grothendieck was, I guess, most active in the 1960s. He had a slightly complicated history, and I think I never met him, but he was wound up at a place called IHES, sort of top French math research institute, and was sort of a big fixture there, and sort of generated a lot of very, very magnificently abstract mathematics, which fortunately for him was fairly well appreciated. It might not have been. It might have been like people just say, we don't understand what you're talking about. But no, it was quite well appreciated. But then I think he got rather disenchanted with things. He kind of went, as happens, from kind of thinking about pure mathematics. He started thinking about kind of the structure of the world and applying kind of pure mathematical thinking to the way the world should be set up. And that doesn't usually end well, because the world really doesn't seem to work like kind of the kind of abstraction and perfection of pure mathematics, so to speak. And so people got kind of annoyed with him, and he then went off and started hanging out in the sort of rural France, more or less, and lived out many years. Unclear quite what he was doing, but it's kind of an epic sort of tale of reclusiveness, so to speak. But in any case, during his sort of golden years of producing mathematics, he was producing extremely abstract mathematics in this particular direction. A different branch was the development of category theory, which started with folks like Saunders Mac Lane in the 1940s. Category theory is another kind of way of thinking about sort of the sort of an abstract representation of mathematics, where you're just saying sort of how do things structurally fit together, rather than this is a particularly a polynomial or a triangle or something like this. But it's kind of what is the kind of flow of these concepts connecting with each other. Now, it turns out that sort of higher category theory and Grothendieck's work kind of merged together at some point into a sort of a blaze of abstraction. I have to say, for myself, I had thought I'll never kind of need to know about Grothendieck's more abstract work, except it turns out that this thing that we kind of developed that I call the Rulliad, this kind of entangled limit of all possible computations, is also something that is essentially aligned with the most abstract thing that Grothendieck produced, which is what he called the infinity groupoid. And it's kind of a strange thing that this most abstract output of our efforts with our physics project and so on, and thinking about computation, has sort of merged with the most abstract efforts of this kind of pure mathematics. And Grothendieck's main idea and conjecture is that in this infinity groupoid, there is sort of an inevitable geometry to this thing, which is very similar to what happens with the Rulliad and the inevitable emergence of physical space and so on from that. This is a long story to try and explain this in more detail, but that's kind of one direction there. Now the question was, has all of Grothendieck's work been understood yet? I think the answer to that is probably more or less yes, although I certainly don't know every corner of it, and that it was quite voluminous. But this real pinnacle of the infinity groupoid and so on, and sort of its merger with higher category theory and such like, I feel like that's something which, again, I had thought I would never personally care about, but it's something that has, again, merged with a lot of the abstract things that have emerged from our physics project and so on. Let's see, questions here about let's see. Question from O. Lemon about what was the earliest use of radioactivity for light, heat, and so on. I mean, I think radioactivity, in terms of uses of radioactivity, big use of not quite radioactivity was X-rays. In 1900, I think, Röntgen discovered that what you got by crashing electrons into some target and getting something, in fact, X-rays, coming out that let you kind of like see through hands and so on. So that was one application, not precisely radioactivity. Then there were things like radium dials. This was a not very good idea, that radioactive element, discovered by Marie Curie, was something that has a pretty long half-life, so it survives a long time, but it keeps on emitting radioactivity. And those radioactive particles have when they crash into other atoms, they excite those other atoms, and those other atoms can produce light. And well, particularly when you have some fluorescent dye and things like this in the picture. And that led to the idea of radium dials for watches and things which glow in the dark. And when I was a kid, for example, in the 1960s, those were still around. They were probably a profoundly bad idea, because it's like radioactivity is not the same particles, radioactive particles that produce those flashes of light also will destroy the DNA in your cells and so on if they interact with that. But I think sort of the whole kind of story of the applications of radioactivity, I think by the time there were alpha particles that were, that's one of the sort of channels of radioactivity, those were used for many scientific purposes, like discovering the nucleus by scattering alpha particles from, and seeing that sort of most alpha particles, when they went through kind of a gold foil or something like this, just pretty much went straight forward. That was Ernest Rutherford's experiment. They pretty much just went straight through, but just some of them would hit something hard and they would bounce back. And that was sort of how the atomic nucleus was discovered. Many years later, in the 1960s, late 1960s, sort of a similar thing happened, where people observed, actually this was beginning of the 1970s, that this was finally sort of clarified, that when you bombard a single proton with a bunch of electrons, then again, the same kind of thing happens, that usually the electrons just sort of more or less go straight through, but occasionally there's what was called deep inelastic scattering, large momentum transfers. The electron would bounce off something that seemed to be a hard thing inside. And that was what initially around 1970, they were called partons by Dick Feynman. And sort of they've been hypothesized quite separately by Murray Gell-Mann and so on, that inside protons there might be these things called quarks. And it became, by the mid-1970s, and this is something I was a bit involved in, it became clear that sort of the partons are in fact quarks. The hard bits of a proton are these seemingly point particles that are sort of are the constituents of protons, just as the nucleus is the constituent of atoms, so to speak. So it kind of was a case where history sort of repeated itself. But the real uses, I mean, there are many uses of radioactivity that have been discovered at different times, whether it's for carbon dating, for using the fact that when in the atmosphere there are most carbon atoms in the atmosphere are carbon-12, but some are carbon-14, and that happens because cosmic rays, mostly from the sun, hit carbon atoms and or hit other kinds of atoms and end up with this slightly radioactive form of carbon. And if you're a tree, for example, and you're ingesting carbon dioxide every day, you ingest some of that carbon-14 from the atmosphere. If somebody cuts down the tree, you stop ingesting carbon-14, and the half-life is what, a few hundred years, I think. I don't know, maybe 1,400 years or something, I forget. But in any case, once the tree is cut down, the amount of carbon-14 in it will gradually decay off, as opposed to being continually replenished because the tree is getting carbon-14 from the carbon-14 in the atmosphere. And so this was discovered as a way to date things like trees, wood, whatever, through radioactivity. There are other forms of dating that work with radioactivity, various, I think, potassium argon fission track dating. I think that's dating by using, again, the fact that there are some small amounts of radioactivity that get produced, for example, by cosmic rays, and that's one I think particularly useful for pottery. That before the thing gets kind of set, it's still ingesting these nuclei which are radioactive, and then afterwards they just decay. Well, there are lots of kind of, okay, another sort of use of radioactivity had to do with understanding the heat of the Earth. Why is the Earth hot inside? Well, for a long time it's sort of debated. I think Rutherford claimed it's hot inside because there are radioactive elements that were created at the time when the Earth was created, and they haven't all decayed yet. For example, uranium has multi-billion year lifetime, and so it has uranium-235 has a shorter lifetime than 238, but it has it's sort of still decaying, and as it decays, it produces energy. It releases things with high energy that heat up the surroundings, and that's sort of one theory for why the Earth is hot inside. The other theory is just it was hot when it was formed and hasn't all cooled off yet. I think current belief is that both of those effects are there in roughly equal quantities, but that was a long time discussion of kind of why would the Earth be hot inside. And obviously the big application of radioactivity was to nuclear power and nuclear weapons, and that kind of emerged in the 1930s as something that began to be understood, and the idea that one could have both spontaneous radioactivity and one could induce radioactivity by, for example, taking the particles like neutrons that had come out of the first radioactive decay and having them induce more radioactive decay so that one got a chain reaction, either slowly for a nuclear power station or very quickly for a nuclear weapon. Let's see. There's a question here. What current technological advancement will be most beneficial to ancient societies? Gosh, I mean, an awful lot of the technology we have today is built on top of a huge tower of capabilities. I mean, you don't get to make a Roman iPhone very easily. I would think that there are things like antibiotics that would probably have had a huge effect on kind of quality of life. And their supply chain is not so complicated. It's more kind of just knowing, well, penicillin was discovered by Fleming as, I mean, it's one of these typical stories where it's just like he left out this moldy bread and then noticed that the bacteria he was growing didn't like the pieces of mold that were there, and then sort of concluded that that meant you could use kind of mold as things that came from mold, which turned out to be refined as penicillin, as a way to sort of kill off the bacteria. I think the true story there is considerably more complicated. And as is often the case, the kind of one, gosh, now I noticed something story is really a story of kind of a long development of different kinds of thinking. And then you notice the amazing particular thing. And then you realize, yes, this is how things have to work. It's kind of interesting that even in current times, the idea of using, sort of leveraging the antibacterial properties of things like molds, funguses, things like this. This is very much a currently interesting topic, and people are kind of, doing things like going through the complete literature about every, fungus that might have existed, and then trying to use, modern machine learning methods to figure out, what might be relevant as a possible antibiotic source and so on. So this is a story that, even though it originated, I guess, in the 1930s or even 20s, is still a very active story today. But so that would be one example. I think in terms of other, I mean, so much of modern technology is built on this big stack of capabilities of doing precision engineering and this and that and the other. I mean, I think that if we look at the early stages of what led to modern technology, things like the invention of steam engines, the invention of various kinds of spinning and weaving technologies and so on, these are things that kind of launched the Industrial Revolution, and well, also the discovery of which, people, the how do you get, you can mine coal and do things with it and so on. But I suppose, there's a question of if instead of recapitulating the actual history of human engineering development, if you could just go from today, jump ahead, and then go back, what would you be most successful with? And I do think that when it comes to conceptual ideas, sort of the ideas of computation, the theory of computation, so to speak, the notion that you can set up these systems of rules and kind of deduce what happens from them and think about that abstractly, that's something that people were pretty close on in the 1600s. Like Leibniz was pretty close on that in the late 1600s, didn't quite get there. And in the end, it took a whole chain of development of mathematical logic and so on before people were quite positioned right to get to people like Moses Schoenfinkel and Emil Post and Kurt Gödel and Alan Turing and so on in the 1920s and 1930s. And that was, it was sort of, and then this abstract notion of computation emerged, which really was something that could have been discussed back in the 1600s, but wasn't because people didn't think of it. Building a computer, quite different story. I mean, building an electronic computer, just a huge stack of kind of engineering capabilities. I mean, I think when Charles Babbage, sort of as interpreted by Ada Lovelace, were thinking about the analytical engine back in the 1840s, that was going to be a giant. They called it the analytical engine because it was like a locomotive, like a steam engine, a giant mechanical device that could do computations. Never got built, but that was something where the concept of that as an abstract piece of computation, Ada Lovelace was sort of the closest to that idea, but one could have taken that abstract idea and kind of run with it, independent of the actuality of making this giant mechanical engine to implement it. But so I think that would have been something that, had that existed in the 1600s, the idea of computation, calculus, for example, would not have been the only game in town in kind of formalizing science. And that would have probably been a very different history. And I think we would have had, well, many things that are just now beginning to be understood and developed, including lots of things I've worked on a lot, that come from this sort of computational paradigm would probably have arisen much earlier. But it's always this very difficult thing to take all the details of what's going on and abstract from it to something like the abstract idea of computation. In fact, I've just been thinking about some things recently where I'm quite certain that there is an abstraction that is kind of a little bit like kind of the abstraction of information theory or something. It's an abstraction that once you see it, it's going to be really obvious. But getting to seeing it is not easy. And that was kind of the story of computation, and the getting to seeing it was a multi-hundred-year adventure in that case. And in the case I'm looking at, I'm sort of hoping it's going to be a months rather than centuries kind of proposition. Harry is commenting something I don't know much about. Getting to significant industrial scales was really hard for penicillin. I don't know. I mean, it's a general feature of engineering that sort of, first you get it to work and then you get it to work smoothly. First you get you can make one of it and then gradually you improve the yield of what you're making and it becomes more viable. I mean, I know something I sort of really noticed was back in the 1980s, I had seen flat screen televisions. It's like, okay, there are going to be flat screen televisions everywhere, but there weren't. And the reason there weren't is because to make a flat screen television, every pixel has to work. And the failure rate of pixels was high enough that to make that one successful flat screen television was just, you had to scrap an awful lot of, candidate ones that you manufactured that had some pixels broken. And it took a decade and a half before that got to the point where enough were working that you could really economically manufacture these kinds of things. And I think that's true of most kinds of engineering processes, that, when you start it, you just get something to work and then you progressively refine it to make it better and better. And I don't know the details of the making of something like penicillin, but I'm sure it worked in something of the same way. Let's see, just a couple more things and then I should run along here. Let's see, Cody is asking, what kind of technology present today do you see becoming nothing more than history? What are examples of previous technologies that have been discarded? Oh gosh, I mean, I have a whole collection of weird computer-like things that people made at different times. One of the things about discarded technology is it has a terrible habit of coming back. There were the computers that sort of had two pieces that unfolded. One was the display and one was the soft keyboard. And that seemed like it was a goofy idea, but it's coming back. Or kind of the notion that kind of the idea of do you centralize computing or do you have it be kind of personalized edge computing type thing? And that keeps on oscillating back and forth. So, I don't think these technologies that another great example is virtual reality. I mean, I first played with one of those systems around the late 1980s, and it was like, this is going to happen real soon. And, finally now we have sort of pretty good virtual reality type hardware, not completely clear what the sort of use cases that are really going to be strong that develop from it are. But it's something where it was kind of like, you might have said, oh, it's dead meat, never going to happen. But actually, it's eventually going to happen. I mean, there are things where you look at it and you say, that's really a bad idea. Maybe at the time it is, maybe with the way it's been built at that time, it's a bad idea. I mean, I'm reminded, I have a cover of a Scientific American from This must be from about 1900. And it has a picture of a guy with steam-powered roller skates. And it basically says, our steam-powered roller skates are the way of the future. Well, obviously it didn't work out that way right then. But, you see people with all sorts of different, personal locomotion devices that do or don't work out. Another good example of this was the Segway sort of gyroscope adventure of the wheeled object that you could just sort of lean forward on, and it would go forward and it would keep its balance and so on. Kind of a derivative, I think, of various kinds of go upstairs wheelchairs and other technology like that. But that seemed like a really cool thing, and for some case or another, you see them occasionally, but they didn't take off the way one might have expected. Now, will they take off in the future? Maybe yes. I think it's hard to know. I think that the amount of technology that's just, this was a bad idea, let's just not do it, is perhaps not so large. It has a habit of coming back. I suppose a case where this does happen, where it's like various kinds of medical interventions, oh, that particular piece of our physiology isn't important, let's take it out, type thing. There have been a whole series of episodes of that, where it's like, we don't know what it does, it got infected, let's take it out, type thing, has been, or it's doing bad things, let's take it out, kind of thing, has been. That's a case where there are kind of theories that, those are more biological theories, biomedical theories, where they just turned out to be a bad idea. And usually the reason they turned out to be a bad idea is because the absence of knowing what something is for doesn't mean it isn't for anything, so to speak. It just means you don't know what it's for yet. And so that's one case where I think things that, and I could guess about some things now that people do or don't do, for example, for medical purposes, or where people will eventually say, that was just a really bad idea. Throwing this drug into this situation was just a really bad idea, because it was, you thought you knew what it was doing, but in fact it was doing lots of things you didn't know it was doing, and so on. So a few comments there. I don't know what, in terms of kind of well, things, I mean, there are so many of these, is it a good idea, is it a bad idea type things. As I say, the amazing thing is that these ideas come back. Most of these ideas come back. And, whether it's the quadcopters, which people looked at, I don't know, back in the 1940s and so on, couldn't make them work at that time. Eventually, batteries are good enough and control systems are good enough. Yes, you can make a little quadcopter drone and so on. All right, I should probably wrap up here, but thanks for joining me, and I will hope to see you on another live stream sometime soon. So bye for now.